Let us learn the formula for total number of reflexive as well as symmetric relations. Its formula is 2 raised to the power n into n minus 1 upon 2. Now let us see how does it happen, and we will deal it with the set containing two members, that is let A is equal to 1 and 2. So here again L is 2. So according to this formula, what you will see, 2 into 2 minus 1 upon 2, 2 cancel, means there will be 2 raised to the power 1, that is 2. Let us see how to find out this relation. Reflexive as well as symmetric relations. First of all, we will find out A cross A elements, because relation is the subset of A cross A. So that is 1 1 1 2, yes, and 2 1 2 2. Yes, these are the elements in your set A cross A. Now reflexive as well as symmetric. What can it be? One your set can be which is reflexive as well as symmetric. So for reflexive you have to have 1 and 2 2 must be there. Okay, and to be symmetric there must be 1 2 and 2 1. Okay, this is the one possibility, and another possibility is that 1 1 and 2 2, because 1 1 reverse 1 1, 2 2 reverse it 2 2. So this relation is both reflexive as well as symmetric, and the first relation is also both reflexive and symmetric. So there are 2 in total: reflexive plus symmetric. So you can see that formula is also saying the same thing. Now we will derive this formula for the n numbers, how it is happening. So let us see how it is happening. You have A is a set which is containing 1 2 3 dash 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 n elements. So A cross A will be containing elements as 1 1 1 2 1 3 dash 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 1 n. Then 2 1 2 2 2 3 2 n, 3 1 3 2 3 3 3 n, and similarly n1 n2 n3 dash 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 n. Yes, these many elements will be there across it. We have to find the number of reflexive as well as symmetric. Now you already know about the diagonal elements, which are the first and second entry are same: 1 1 2 2 3 3. And elements reflexive elements type of, you already aware of that. So what happens is, now your set must contain those elements which is reflexive. Means 1 1 2 2 3 3 n n has to be there. Means they have no choice other than to be present, and these are in n numbers. So what you will say, that each of these n numbers has to have there, and they have only one choice. So into 1, and this is how many? N times. Now you have to deal with the numbers which are above the diagonal and below the diagonal. Now you already know that above the diagonal elements and below the diagonal elements, they have the numbers which are in pair and which will give you a symmetric relationship. Yes, all the elements are having just the reverse of these many elements. Okay, so we will consider these two elements as single elements. Okay. Now you already know that diagonal elements are any number, and above the diagonal numbers and below the diagonal numbers, if you make it together, you will get n square minus n elements. Why? In totality, A cross A contains n square elements. So A cross A will have n square element, and diagonal elements are any number. So remaining numbers are n square minus n. Yes or no? But we will take the half of that. Why? Because every number in the above, there is its reverse number in the below side. So we will make it one entity. So in this way, you will have n square minus n by 2 total pair of those numbers, which will give you a symmetric relationship. And all this has to have there, or they may not be there. Okay, because all the reflexive relation is a symmetric relationship. Why? Because 1 1, if you reverse it, 1 1, so all the reflexive relations are symmetric relationship. So there is no problem if the set is containing only the elements which are type of reflexive elements. Okay, so either 1 2 or 2 1 will be there, or they will be not there. So each of such pairs have two choices, and how many up to those numbers are in how many numbers? These numbers are in how many numbers? In counting, there are n square minus n times. Okay, so now you multiply it into 2 raised to the power n square minus n by 2, sorry, by 2, half of that, because we will take the pair 1 2 and 2 1 as the one point, one entity. Okay, so that is why I'm doing the half to half. So when you will calculate this, you will get 2 n square minus n upon 2, that is 2 n common n minus 1 upon 2. This is the formula for total number of reflexive as well as symmetric relationship. Now if you have 1 2 3 three elements, then how many number of reflexive as well as symmetric relations? If you will put it in the formula, 2 3 3 minus 1 by 2, so you will be getting 2 3 into 2 by 2, that is 2 power 3, that is 8. Okay, in this way you can find out. And again I am repeating the thing that till now we have not get the formula for no formula for transitive relations. But if you want to remember it, then for n equal to 0, there is one relation. N equal to 1, there will be two relation. You can remember it. Transitive. N is equal to 3, you will have 13 relations. Okay. N is equal to 4, you have 171 relations, and you can remember it only. And for the equivalence relation, I have already given you in my shorts that it works like this. Suppose you have in a set containing one element, then there will be one element. Okay, for 1. In a set containing 2 elements, it will be 1 and 1 plus 1, 2. Then this 2 comes here. For a set containing 3 elements, 2 comes here, 2 plus 1, 3, and 3 plus 2, 5. Then 5 comes here. Then 5 plus 2, 7, 7 plus 3, 10, 10 plus 5, 15. This is for the 4. In this way it works. Again 15 you brought it. 15 plus 5, 20, 20 plus 7, 27, 27 plus 10, 37, 37 plus, okay, 2. This way, this gives the number of equivalence relations, where this number is giving you the number of equivalence valence relation, and this is called bell tree. In this way you can find out. Thank you.